Hello, everybody. Welcome to this talk about choosing a hardware components from a software point of view. So I'll just introduce myself. So my name is Jeremy Rosen, and I'm a Linux engineer since 1997. I have been doing this nonstop since I finished my studies. Through my life as a Linux engineer, I've been through all sorts of open source projects, and nowadays I'm more and more on the integration side of embedded system, which is basically making the Linux system work as a whole, more than actually developing the application. And so I've been more and more focusing on the kind of project of problems embedded project have as a project, because as the expertise manager at Smile, I've been dealing with that sort of problems a lot. So a little word about Smile ECS while we're at it. So Smile ECS, which is the branch of Smile I'm part of, is specialized on embedded and connected systems. So we'll be mostly speaking about the embedded aspect here, but we also do all the IoT problematics with connecting, onboarding, and stuff like that. But that will not really be the subject today. We are about 80 consultants, including 11 that are tagged as expert in various technology we use throughout our projects. So kernel, Yocto, Buildroot will be the ones we will be mostly talking about today. But again, we have more than that depending on our needs. We are rather big. We do more than 50 embedded projects per year throughout the company. And because I'm managing all the expertise, I more or less see all the projects we have, which means I have a very transverse view of what's going on, and I have an eye on new problematics appearing and hopefully old one disappearing, and how the industry is moving, which I can see through the requests from our customers mainly. So there might be a bias here because our customers are mainly industrial customers and more than B2C type consumer customers. But still, there are some trends I try to see early, and usually I do a talk about them. And in a way, this is the base of the talk we have here. So what happened is in the last couple of years, mainly since in 2021, but that was something I've had already seen before. We have customers that are coming to us asking for a new kind of expertise, if you will. So what's happening is we have customers that are asking for help in the hardware design phase of their products, and that's pretty new. Usually, we had customers that would come to us once their board was designed and sometime even produced, or at least they were waiting for the prototypes, and they were going on the line of thought that now that the hardware design is done, it's time to try and look at the software part of things. So we take the software expert and we bring them in. And so since a couple of years, we have more and more customers that are asking us to come early, so as an expertise, not as a full-time consultant, to look at the software side of things when designing the hardware, just because they have been bitten once and they know that some hardware choice can have huge consequences on the time and the cost of the overall project. So we are here to do risk assessment. So that's basically taking the development board and making sure that the software is able to do everything that will be needed. So it's not developing the final software, it's checking that the hardware plus software stack will be able to deliver what is expected. So we also help with hardware choice. So when I say expertise in hardware choice, I don't mean doing a hardware related assessment, but really a software related assessment. So I am not able to talk about stuff like electromagnetic compliance or power consumption or how hard it will be to route or end of life of different components. However, we come here to check other things like are the driver here, are they up to date, do they follow best practices, how hard will it be to upgrade. Those are things that the hardware forces on us because we have to use drivers that goes with the hardware, and that can have great impact on software quality. So we end up having to look at what's available in BSP when we start a project. So we also end up being invited in various discussions with hardware providers, so board designers, to a lesser extent with sock makers, but that's less common, to assess their software practices, to audit their plans to support their BSP, especially with long-term support, which is a real problem in software. Nowadays, hardware have very well-defined plans with hardware availability, but those same people that have great plans for hardware availability have no publish roadmaps for software upgrades. And with software upgrades comes product security. So it's pretty important to assess that those sort of things work. So what I want to do in that talk we're here today is really help you do it without us in a way. I mean, when I assess the quality of a BSP, I end up doing things that are pretty simple and that anybody can at least get without the worst case easily, like checking if things compile and stuff like that. And I would like to one convince you that it's useful, and to give you the simplest lines and main point of interest if you want to start doing that yourself. So first, why this is really important. The first thing to understand is that drivers are hard. Okay, so if you have drivers that works, that provides everything you need, all the features, that is well written and well integrated, we don't write drivers because they're already here and we're happy and the cost is null. However, if your driver is missing a feature or if your driver is available for the wrong kernel version, then we will need to write new features or even a complete driver, or port a driver from a kernel and to another kernel. And both those actions are far from free. They are hard, long, and costly. Hard means that you need an expert. It's not something that can be easily done by any developers who knows C. You have to really understand how kernel work, because moving code from a version to another is easy. Figuring out why it doesn't compile and worst, why it doesn't work can be very tricky. And if you port through a large number of kernel versions, then it's actually not a porting, it's more like a rewrite, because the internal API of the Linux kernel are, well, I think we can say they are guaranteed to change. So there will be lots of work. It's hard, you need an expert. It's long because it's not trivial. There is a lot of testing, lots of wasted time while we try things that don't work because before finding the magic combination. And as a result, it costs a lot. It costs a lot in time and in money because we have an expert, he's expensive. And so it's important to know where you're going so you can put that in your planning and in your overall project layout. Okay. That's the first reason. The second reason is sometimes you have a component which is gloriously featureful on its data sheet, and when you start using it, the software guys come along and say, yeah, but it doesn't work like it's supposed to. And what happens is some component makers try to add value, if you will, by providing extra API or non-standard API to pilot their component. And the big result of that is that you're stuck with that component and that your team, which is used to working with standard components, will have to relearn everything to work with your non-standard components. So non-standard API increased development cost because your team has to relearn, and also greatly increased evolution cost because the day where you have to change your component, unless you take a component from the same family, and even then that's not a given, you will have to go back to the standard API. So you will have to change how you use your component. And if you change how you use your component, then you will have to rewrite a lot of stuff. So that's a bigger cost. Uh, and last, one of the big reasons, so those sort of non-standard API are very easy to find if you look for them. And to look for them, you have to test the software. So that's something you can do early. You can do before choosing your actual hardware. So that's easy to avoid when you know the trap. And last, there is a real problem in Linux with unmaintained drivers. So here I'm not talking about mainline drivers, which usually are very well maintained, but lots of component maker don't go to the trouble of mainlining their drivers. They just provide you, the customer, with the driver, and they do not provide it to the community, which means that and the reason for that is that upstreaming a driver costs a lot, and they don't want to go through the cost. So obviously, it's not because you pay to get a driver in Linux; it's because because it takes a lot of time, because the quality control of the Linux maintainers is very harsh, and overall they just are fine with a driver that works without having a driver of high quality. That means that they don't upstream their driver, and worse, they usually don't update their driver. That is, they develop their driver for a given version of the kernel, usually a long-term support version, but they do not touch their driver once they have a driver that works on a given version of the kernel. The problem being that most long-term version of the kernel will not have the same lifespan as the component, and the days your long-term kernel is end of life, your component will be as good as dead. Because if your component does not have an up-to-date driver, you cannot update your kernel. If you cannot update your kernel, you might as well not do any security updates because your system will be vulnerable, and so your whole product will be end of life. That's something you need to assess. It's something you need to ask. Okay. So before I go into how to check for those things, I'm going to do a little bit of generic discussion about how the hardware and software ecosystem works. So probably those are things that you know, and I will just be putting words on stuff you know. I will also try to talk about the different actors and how they try to make money in the ecosystem, because that's a bit important to understand what's going on and why drivers are not updated properly, and why you need to make sure that your driver will be updated properly throughout the whole life of your product. So something that, kernel developers know, but hardware engineers usually don't know, and that's pretty important for them, is that in the Linux kernel, the support for a given piece of hardware can be cut into more or less independent halves. You have the device driver, and you have something else called the device tree. Okay, so I will not go in any way into the technical aspects of what are those two things. Let's just say that the device driver is kernel code that knows your hardware components. So if you have I don't know, an I2C sensor, This will be the piece of code that will read the sensor's registers and interpret them and say, okay, so I've read 0x24. 0x24 means that it's C degree outside, so I will write 50 in sys class, blah, 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 so people can read the temperature. Okay, so a device driver is actual source code that pilots the component. Okay, it's really specific to a component, and well, unless you have multiple components of the same family, you usually have one driver per piece of hardware. And and so it's something that is written by someone who needs to have very intimate knowledge of the hardware components. So it's usually written either by the component maker themselves or by a subcontractor for the component makers, but it's usually not written by a third party because it needs to really know the component, and so the reverse engineering effort is huge. You have some volunteers that do that for some components, and they do an incredible job. But the most common case is that it's written by the component maker. Okay. A device driver drives the component but does not know how the component is connected on your board. So if I stay with my example of my I2C thermometer, the driver code knows that it's an I2C thermometer, and it just asks the kernel, oh, I need to get that register on that I2C device, on my I2C device, but my I2C device is all that the device driver knows. The device driver does not know where the device sits on what bus and at what address. Which brings me to the second half of your piloting of your hardware, which is a device tree. Okay, so the device tree is a kernel readable description. It's not code. Okay, it's a description of the board schematics. So it's basically a data structure. So you can have it in text or binary formats. The both exist, and I won't go into the details. But basically, what's important to remember, it's just a software equivalent of your board schematics. So just like your board schematics, the device tree describes what components you have and how they are connected. So if I get back to my I2C thermometer, your device tree will say that you have a thermometer of class X, which is on I2C bus 2 at address 0x3c. Okay, and with that information from the device tree, the Linux kernel will find the right driver and will feed the right driver with the data about the actual position of the component on the board. So when you assemble both together, you have a device driver that can find its device, and you have a device tree that can be easily changed if you move the device on the bus. So that's pretty interesting because device trees are easy to understand and to edit by hardware engineers and board designers. What I mean by that is that the way things are described in the device tree is very close to how you do board schematics. So the semantics, it's another language, you have to learn it and so on and so forth. But the philosophy of the thing, the content is closer to a hardware board schematic than to a driver. So, and also device trees are meant to be loaded at boot time and understood to be editable at boot time. So your bootloader can find multiple device trees and somehow choose the right one and maybe edit partially the right one depending on what it finds. Which means that overall, for a software developer, changing the device tree is easy. You can have multiple one, you can choose them at boot time, you can change them. It's all pretty trivial. So if you have a board and you move the components around and you reroute your board and you change the address of every component everywhere, your software engineer will be, yeah, do your thing, no problem, we'll just fix it in software. And it will be trivial, and basically the day your board will be out, you will have your corresponding software image and everything will work because changing the device tree is easy. However, the second case, changing a driver, is hard because as I said, driver needs to be very intimate with the component, and that's where we reach a first trap, which is the pin compatible trap. So pin compatible is a word that hardware engineers love, and they love it for a very good reason, because it makes things extremely easy for them. Two components are pin compatible when basically they are equivalent from a hardware point of view. So you plug them one instead of the other, and all the clocks will be the same, and all the power lines will be the same, and you have no problem of impedance online and stuff like that, because all this works the same. So hardware engineers love those components because you don't need to redesign or reroute your board. When you need to update a component with a pin compatible one, you just basically change the box of components that is delivered to the factory, and people just take their components from the other board, solder them on, and bam, you're good. From a device tree point of view, if you change a component with a pin compatible one, there will be some few tweaks with the device tree. Usually not too much, because basically you change a component and a device tree tells what component is on the board. So you have to change the device tree so the kernel chooses a new driver. And that's when things start to go bad from a software point of view, because the new component has a new driver. As I said, the driver is the hard part. It's the part that's completely different from one product to the other. So as a consequence, because we have changed the driver, we need to have changes, heavy changes in our kernel. And this thing tends to have a cascading effect of consequences in our software stack, which means that a component where the hardware engineers come and say, oh, it's just an upgrade, we put a new component, it's a new version, it works exactly the same. And then the software engineer comes behind and say, oh, yeah, but it doesn't have the same driver. The new component, its driver was not added, was added to the kernel only recently. We have a very old kernel, because we have a kernel which dates from the old component. Can we port the new driver to the old kernel? That's hard. That's very hard, because we might as well rewrite a driver for the new component in the old kernel. So maybe we could instead upgrade our kernel. Oh yeah, but if we do that, we need to upgrade our whole stack, our whole distribution. You will just change all the thing. Okay, so maybe at least we can save our user space main application. Maybe, maybe not, because sometime when you upgrade your whole distribution, well, your dependencies go up to date. So if you go from Qt4 to Qt5, for example, you might as well rewrite everything. So we have a component which, from a hardware point of view, is a, well, I was going to say a hot swap. It's obviously not a hot swap, but pretty trivial to change, and the cost is huge on the software point of view. And if you remember what I said in my previous slide, if you have a very complex change which has a whole rerouting on the board, it's pretty trivial to change from the software point of view, because it's just device tree. So this is a trap I had many customers fall in, which is the idea that something is pin compatible, so we just change it and the new board come out of the factory and they don't boot. Oh, what happened? Well, we didn't change anything. Did you really? Well, that was this component, but it was pin compatible. Oh, okay, we'll have a look, and we check, and we realize that there is actually borderline a complete rewrite of the system because of a component which was supposed to be pin compatible. And since it was supposed to work magically, we end up in the situation where we have an unexpected emergency upgrade of the whole software stack, which hasn't been budgeted neither in time nor in money. And your boss is very unhappy, and we do our best to help, but we're always seen as an extra cost, and it's a pretty nasty situation. So yeah, if you have to upgrade a component, check the software consequences. Don't go blindly at it. So that was for the software side. We have device driver and device tree. And now for the hardware side, The hardware we use usually have a sort of Russian doll pattern. That is, you start from a SoC, which is a single processor. You mount it on a SOM, system on module, which is a couple of tightly dependent components, and then you put everything on a board, which is either a dev kit, development kit, or your board that custom made. So we'll see those different stages one by one. So the heart of your system is called a SoC, or system on chip. So again, I won't go too far in the detail. It's not really important for our talk today, but it's basically your CPU. So it's a chip that contain all the processing power of your board, plus the chip also contain hardware acceleration for a very large number of functionalities, being Ethernet. Sometimes they have Wi-Fi accelerator, Bluetooth accelerators. They have their all sorts of internal clocks. They have I2C buses, SPI buses that goes directly out of it, USB ports directly inside the chip. So those chips, those CPUs, are pretty complex, and one of the problems they have is that they don't have enough pins for all their functionality, so you have to use only some of them on a given board. But that's really not really important here. So who builds SoCs? There are a very little number of manufacturers, and building that kind of chip is extremely high tech, extremely expensive, and so with very expensive R&D, very expensive factories, and so I don't know how many SoC makers are in the world, but probably less than a dozen, and they make their money out of volume. And when I mean volume, I mean huge volume. I mean, they're basically right now there is a little crisis because they can't provide enough SoC for everybody, and car makers have trouble getting their SoC because they don't have enough volume. Card makers, they only produce a couple 100,000 a year, so it's not worth it for the SoC maker to go and talk to them. So that's pretty important because it means that you, with a small project, I mean, at the scale of a SoC maker, I'm pretty convinced all my customers are small. They usually don't care about you. You will have huge problems if you ever need to have support from those guys, even if you pay for it. Usually, paid support from SoC makers doesn't work very well. We at Smile don't have any support contract with any SoC makers, but with some of them, we actually have better support than the paying support, just because we usually come with interesting problems on open source channels, and so the developers there answer. But it's really tricky and really something you cannot rely on. On the other hand, they are the ones that are responsible for making sure their SoC is supported, and the only way to do it rationally is to upstream it as much as possible and be as generic as possible. So that means that the kernel side support of those SoCs, being drivers for the SoC themselves, or the chunks of device tree that describe the SoC and their pinouts and stuff like that, all those are usually relatively good quality. Of course, it varies a lot from the SoC maker to the next, but overall, they have a great incentive to upstream everything and to make everything work as easily as possible, if only because that means less support. And also, there are all sorts of libraries and GPU, VPU, and that sort of stuff they provide, but we won't go too deep on this particular part. So once you have a SoC, you have to put it on some sort of electronic board. So, oh, wait, other hardware components. Sorry. So on your board, you have your SoC, and you have other components, and the two are linked together by electronic circuits. So the other part are other hardware components in general. So those will be the components that are driven by the SoC itself. You have some of them are tightly coupled, like RAM, EEPROM, regulators, that sort of stuff. Those basically you cannot customized for your board. You can choose a working set. We'll talk about that a bit later, but there is very little configuration with those. Then you have what I call secondary complex components, which are still components that are pretty complex, that need a complicated driver to work. But unlike regulator clocks and that sort of stuff, the board usually will work without them. So that's cameras, touch screen, network access, audio, that sort of stuff. And then you have very simple components like the one you have, my I2C thermometer will go here, which need little driver and are usually extremely simple and generic. So, who build those components? So there are all sorts of electronic component makers. There are usually people that are really in the hardware electronic side. They are interested in volume again, and usually you will not, unless you build the board yourself, you will not buy those components. It's the board makers that will buy those components. Those people will already be more interested in your particular problems. However, it's important to note that those people are usually pretty far from the Linux kernel world and don't really have a software culture. So when you tell them that a driver needs to be updated because it's too old, they usually will tell you that's not true. They have a driver, that the kernel for their driver is still supported, and you don't get them to move. So it's a bit of a problem. Why? So those are the people that are the ones that usually do the device drivers themselves. Okay, so they are the ones that have all the details about their component, how they work. Usually, we cannot get that sort of documentation, even if it would be cool to have them. So here are a few notes about those work they do. So they write drivers and they should upstream them all the time. If one of the components you have does not have an upstream driver, usually that's true for complex components like cameras and touchscreens, then you need a compatible kernel. Usually they will provide a driver for one version of a kernel, which is usually a long-term support version of the kernel, which means an old version, up to date from a security point of view, but pretty old from a feature point of view. And one of the problem you might encounter is missing features. That is, your component on the datasheet is able to do a certain number of things, but the driver provided does not allow you to pilot those features. So it's important to check that a theoretical feature is actually in the driver, because if it's not in the driver and you're lucky, then it will be expensive, but we will be able to add it. If you're not lucky, we have no idea how to turn on that feature. That feature has been put in other driver for other OS, being a real-time OS or Windows only or Android only. And we can either try to reverse engineer a working driver if we have a working driver, or we can be totally stuck and we cannot help. And the problem really becomes critical if you have multiple non-upstreamed components. I mean, if you have a camera which works on kernel A and a touch screen that works on kernel B, and then you have this problem that you have no version of the kernel where you can get both devices to work, and both of your provider will tell you that it's okay because they did provide the driver and you just have to use their kernel. So that's why, yeah, you try to go with upstream devices as much as possible. But at that point, you usually have to port drivers around from kernel A to kernel B, and well, that's expensive, so you need to budget it. So I've discussed of SOC, we've discussed of the components. Now the first stage of putting those together is called the SOM, or system on module. So what is a system on module? It's a small bit of PCB which is meant to be plugged on a carrier board and which holds the SOC itself and all the components that are needed for early boot, that are highly tight tightly attached to the sock, and well, basically the ones you don't touch and you leave as is. So that will be your memory, ROM, RAM, EEPROM, flash, everything that's related to power, everything that's related to clocks. Usually then you have a DIMM or similar connector to put it on a carrier board. And usually all those components are very hard to debug if they have problems. So it's a good thing that we have those SOM, which means that our customers usually do not have to reinvent that hard and usually little added value part of the design. I mean, using a SOM will give you the same performance than redesigning it yourself, and it's way less expensive. So usually you will buy the sum that is recommended by your board maker, or you will choose your board maker depending on their sum or something like that. But the two are tightly related, so you just choose your board maker depending on the sum. Okay, and they are all ready. So uh, board makers are interested in small volumes. So those people will be way more interested in your product, in what you're doing, and to help you on your particular problems, way more interested in that than your sock maker or your component makers, because they will be the one that will produce you board. So from there on, you have two business models which are equally good, but it's important that you're aware what business model your board maker uses, because well, it can have influences in how you work with them. Some board makers are interested in volume and will make money on by selling you the boards they built for you. Okay, those people usually uh, kind of provide software as a service. So it's usually software development for your board and customization is usually pretty cheap because they make money on the other half. Uh, why not? It's a system that works, and the alternative is board makers that sell your board cheaper because they make less money on the boards, but they will make you pay for a software development. Or you can, of course, use a third party for software development. That's up to you. But it's important to know that both models exist, and in particular, if you're comparing the price of two board makers, you need to take that into account because, well, the board makers are legitimate in making money by providing a service, and everything has a cost. So if you try to cheat and to game the system to pay less, you will end with a very bad quality software stack, and that has a huge cost in long term. So there you go. So those people will help you. That's the good part. And then those people are the ones that will develop the partial device tree for you. So the partial device tree is the SOC device tree plus the part of the device tree that describes the system on modules. So list of the components of the sum is a connection between the components and the SOC, and also stuff like RAM timings, clock configuration, and stuff like that. All that will end up in the device tree. Plus, usually there is a little bit of drivers because this is a very low level, so there is a need to have some stuff on that side. Once you have chosen your sum, you will usually buy something called a development kit. So a development kit is a sum plus a carrier board, and that carrier board is not meant to be specific for your project. This carrier board is here to allow you to test everything the sum can offer. So usually you have the sum itself, which is plugged on, and all the extra components that don't fit on the sum, but are usually needed or need to be tested. So this includes PHY, codecs, SD card, that sort of stuff. And usually those carrier boards also have connectors for more complex stuff, like a USB port, RJ45 if you want to do Ethernet, MIPI CSI to connect a camera, and all sorts of generic connectors for GPIO, I2C, so you can add your own components with a soldering iron and test that they work. So those boards usually buy with your sum, and it allows you to test everything. And usually you have a BSP which is provided by your board maker, and which is here to impress you by showing that everything works out of the box. So it's a rich and easy to use BSP for testing the hardware. It's not usually a very good BSP to produce your final image. Even if it's a basis to build one, it's not something that's easily to make specific. So that's your development kit, which allows you to test everything, and which is the first stage where we have a complete Linux system. And last, you have your board. So the board that has been made for you, that will be built in the factory of your board maker for you, and which is specific to your use case. So on that board, you will have your system on modules. So either you have the same connectors and you plug the sum on your board, or you reuse the schematic of the sum and you integrate it on your board, but basically the sum will be here. Don't try to make your own, because making a sum is hard and has very little added value. So all the components you had to solder on your dev kit to test, you can have them on your board directly. Of course, it has a form factor to fit your product, and we will and the BSP that you have had developed for this SOC is custom. It's minimal. It only supports the configuration you want, and it's pretty good. So who will build that final product? Usually you have it done by the same people you've bought the system on module from, but there are also some independent board builders, which are usually smaller, but usually also highly technical. So they are not as good for volume, but they are better for very specific problems. Or you can also do it internally with your R&D if you have an R&D which is able to do that sort of stuff. And at this point, we reach a complete software stack. So you have your own unique device tree for your board with all your components, etc. You have your own custom minimal Linux image, multiple images sometime, one for development, one for factoring, one for testing, update system, all those problems. You will have your user space software integrated for your specific use case, ready to use, and every aspect of Linux configuration will be integrated in that last image. So we're really at the final product. So I just presented this whole idea of stack from SOC, SOM, and then the carrier board being a dev kit or your specific board, because this has a real impact in how the software works. We've seen and I've discussed that you have the drivers, and the question of who provides them and in what quality is important. And then you have device tree, and as you've noticed, you have a sort of stacking of device tree. That is, a SOC maker provide you with chunks of device tree, which you integrate into a device tree which describe your sum, and on top of which you have a second device tree that describe your carrier board, and the whole thing together is equivalent to the complete schematic, and which allows the kernel to, well, pilot your board basically. So now that we have a good understanding of this whole architecture thing, how do you use that to actually check your hardware and make sure that the hardware component you're going to solder on your board is going to do what you want it to do and not cause problems down the line? Basically, you do the basic stuff, you download and you compile and you check that that works. So first thing you have to do is download whatever is available and see what is available, because that's always the first thing I check, and there are usually a lot of things that go wrong at this stage. So can you download the BSP and the driver? So best case, it's upstreamed. your board maker do not provide anything because everything is upstream. So this needs to have a developer that knows Yocto or Buildroot pretty well, but usually when that's the case, things go flawlessly. If it's not really available, i.e. on GitHub, or do you need an account? Accounts are a bit annoying because it means that you cannot test without being contacted by marketing people. So I don't really like that, but that's not really a problem. It's a bit more of a problem because it means that reporting problems and suggesting changes will go through marketing. So all that makes it a little bit more problematic, but overall it will work. If you need a purchase number, again, it shouldn't by itself make it worse, but usually it's a sign that the BSP is really under wrap, and under wrap mean bad quality. Okay, so it gets, I don't like that. It start to light red lamps in my head, if you see what I mean. And is there a community around? Our question answered. If you have problems and you look at in Stack Overflow, our answers are available. These are signs you need to see as clues about future problems. And then can you assemble everything? Do you have a driver for all your components? So some components usually are not a problem. The SOC are not a problem, but cameras, I2C little devices, if you do something exotic with USB-C, which is a brand new technology, is it supported by the version of the kernel that you have to use? That sort of stuff. So do your components work on the same kernel version that the one your board use? How long will that kernel version be maintained? I mean, some long-term support have been around for quite some time and will be unmaintained pretty soon, but you still see components that are sold with only that version of kernel supported. So the component will be produced until 2030, but the kernel and the driver will only be updated until 2024. So overall, the component will be deprecated in 2024. Okay, is there a driver level documentation? The answer will usually be no, but if you're lucky and the answer is yes, that's pretty cool because it means that we can write a driver. Again, it will be expensive, but at least it will be possible. Then you have to rebuild the BSP. So this is a very important step because you would be surprised how often it does not work. I mean, BSP are supposed to be easily rebuildable. Problem is that usually they have been delivered once and never updated, except the world around the BSP changes and you download your URL change and components get lost on the internet and your IT might refuse that you use a very, very old Ubuntu to build your BSP because it's too dangerous and not allowed on the network. So all that sort of stuff means that it can be very problematic to rebuild the BSP. So these are the main thing I check when I evaluate a BSP. What's in the documentation? Is it just how to rebuild the image, flash it on the board and have fun? That's minimal. That's not always a problem, in particular if there are very little to no changes to the image. That usually can be enough, but that's still a question. Does it talk about tweaking the image, installing other software, changing what depending on the hardware? That sort of stuff is a really good sign because it means that the people that write the documentation actually know what they're talking about. You'd be surprised it's not always the case. And then how much extra tooling and tweaks have been added by the BSP makers? That's a very important question, and usually the less tool, the better. I mean, it seems counterintuitive, but most of those tools are here to automate the first step of rebuilding the BSP from scratch and usually get in the way when you need to tweak it. Sometimes you cannot add a new, if I take the Yocto example, you cannot not add a layer because the tool will just drop your changes. Or you have hundreds of images that interact with each other and you have no idea where to add your custom software. Or you have scripts that run after the Yocto build and will tweak stuff or change stuff in the image and will override your changes. So usually the less tool, the better. Okay, and then can you actually rebuild it? So do you need specific tools, distro, release? I mean, if you need to use Ubuntu 14.04 in 2021 to rebuild the BSP, this is a problem because it means that in the last 7 years, nobody has updated the BSP. Are the build instructions correct? That's not always the case. Are they still up to date? There are some components like repo which need a very new Linux to work. But if the BSP uses repo and is limited to again my Ubuntu 14.04, then you will have compatibility problems. And last but not least, does it actually build? You would be surprised the number of times where we have compilation errors. These can be done due to all sorts of reasons from changes to upstream components, badly tagged libraries, binary only libraries that have not been tested. It happens a lot. So it's important to check that because that will avoid problems. Now, we have built our BSP. We need to check what's inside because BSP is really a generic term and you really never know what exactly is provided inside your BSP. So to do that is a little bit tricky at this point because I don't know if you've noticed, but we haven't talked about hardware yet because all the steps I've done so far are steps you can do without hardware, so without even buying, or if you're lucky, not even telling the board makers you're actually testing their stuff. So what's in the BSP? Do you have a minimal image with just what's needed to build a Linux system, and then you need to add everything your project needs on top of that, or is it a BSP image which contain every possible tool, every possible demo, which allows you to test everything? Both are okay. It's not really a selection criteria, but it's something you need to be aware of. The minimal one will require more work to get your system up and running, but the bigger one needs that you will have a real job of sliming things down and removing everything that is not needed. So how hard will it be to add a missing tool? Is it just a question of telling Linux of Yocto or buildroot to compile one more package, or is everything or every build script has been tweaked and it's almost impossible to understand how it works? I've seen both. For complex components, so JStreamer, OpenCV, OpenGL, Qt, are they available? Are they tested by your BSP provider? Because those components have a bad tendency to break when you change anything in the socks, so it's important to test that they are there. What device trees are available? Are they easy to tweak? That's usually not too much of a problem. And if you can do a quick audit of the kernel to see how much patches have been added and by who, that is a big plus because it will allow you to know if you need to have to audit all that. And last but really not least, really important, how old is the BSP? I mean, if your BSP is like one version older than the latest version or two version older, maybe they just did not update. If it hasn't been touched for years, or if the touch were cosmetic, but the base of the BSP is still a very old version of Yocto/Buildroot, that means that somewhere in the chain of providers for your software, is not doing its job and is not updating whatever part is responsible of. It can be a component maker which do not upgrade their drivers, so you cannot upgrade the kernel, so you cannot upgrade the Yocto version, so the whole BSP is stuck with an old version. This is very important because this is what will limit your possibilities for software updates. If you cannot update your Yocto, then you cannot provide security for your system at all. It's just too much work. It's not possible. So you have to check that. Last, once you have the board, the dev kit, you can do the actual fun stuff, play with the hardware. So testing the BSP itself, so check that all the hardware feature actually works, especially for cameras because they are a complicated beast. Check your performance, check that all your external driver is here. And what's pretty good with Linux is that you actually can do a lot of development on a dev kit or even without a dev kit, because the Linux API to access hardware is usually very hardware independent. So a camera is a camera is a camera, be it USB, MIPI, CSI, or even something you stream over the network. They will all look more or less the same. Linux has lots of software emulation for hardware. So if you want to simulate GPIO, you can. If you want to simulate keyboard and mouse, you can. Buses, networks, all that sort of stuff. Linux has software emulation in the kernel. So if you take some time to put that in place, you can actually do some very complex stuff with that. So that's it. Most of your development you can usually do. You need to be knowledgeable in Linux, but usually you can do on a Linux desktop if you know how to do it. And most of the integration, and in particular adding recipes to your BSP, is something you can do on the dev kit. You don't need the board for much. So software development can be parallelized with hardware development quite a lot because the dev kit arrives early. And last point, red flags. So these are a couple of stuff where when I see it, I know I will have a lot of problems. So the first one would be an Android-oriented BSP. So that's not the same thing as Android support. Android support is fine, Android support is good, but there are some BSPs that are actually Android BSPs that have been adapted to look like a Linux. And that's not good because Android is very different from Linux. Android is not meant to be customized. And more importantly, Android SOC makers don't really care about Linux, normal Linux. And so the support will be really bad. No source code available. So that's really bad because you will need the source code. You will not escape that. So if you have no source code, this will be a real problem at some point, and you cannot realistically recompile a Qt and install on the board and keep it installed that way. It's just unmaintainable. It won't work. Old BSP, old build environment means that long-term support will not work. Old long-term support kernel, be very careful if there is also a new kernel that's very good. If it's the only version of Linux supported, it's a source of problem. And then creativity with toolings and with integration, in particular with Yocto, where BSP makers tend to reinvent new solutions to problems that have been solved in Yocto. So it's really a source of problems. So the more upstream, when you check your BSP, the more upstream, the better. The more recent the components, the better. The simpler the BSP, the better. And don't try to mix stuff from different generation of software. It will be hell. It won't work. So, as I said, unmaintained driver will prevent security, and security means your board is end of life. So when you assess a hardware component, make sure the software is good quality, make sure the software is available, and make sure that the software will be supported for a long time, which include updates. If your component provider does not have a plan for any updates, it's just game over. Thank you very much. I will be in the chat for any questions.